Okay. Oh, sorry. All right, so next thing we're going to talk about after doing, that's still a bit loud, isn't it? What's going on? Triple integrals is how we do a change of variable, which technically we call change of coordinates. Now, before we do that, when we when we covered integration of functions of a single variable, we covered all these integration strategies. Vast majority of them, except for integration by parts, of course, were substitution methods, right? So remember there was trig substitution, inverse trig substitution, basic substitution, half angle substitution, which we're not really going to do too much of. But essentially, doing a substitution in an indefinite integral for a function of a single variable is motivated by we've got something we can't integrate, right? And the aim of the game with these is to make it into something we can integrate. The fact that it's an indefinite or a definite integral makes no bloody difference, right? It's motivated by the function we're trying to integrate. Now, of course, as I said though, there's no such thing as an indefinite double or triple integral, right? So these are all numbers. They're volumes of some description, depending on what dimension we're sitting in. But when we do it with a function of a single variable, although we usually do it, we let u equal some function of x, and then off we go. But formally, this is what we're doing. We're replacing x with some function of u. We don't normally do it, we usually do it the other way around, except for the inverse trig substitution. Remember, if you've got a square root of a squared minus x squared, you let x equal a function of u, but everything else we let u be a function of x, motivated by what we're trying to integrate. But formally, this is what we're doing when we do a change of variable, right? We let x equal some function of u, and we basically whack this thing in here, and you'll notice that these du's cancel, just like the trick we do with the chain rule. The main thing is, although we don't do it this way, this is actually what we're doing with a function of a single variable. And the main thing to take note is how this is written. Notice it's written as f, the function with x replaced with some function of u, multiplied by your expression dg du, which is now a function of u because we're doing it backwards. Normally we do it as a function of x times du. The main thing is to take note of how that's written, right? Because we're going to now do this with double integrals. But the thing with double integrals, it can be motivated by what you're trying to integrate, but more likely and much easier from our perspective is it's motivated by the region we got to integrate over that will determine our change of coordinates, right? So let's say we've got a double integral, dx dy or dy dx. We know now the order makes no difference. Let's say we've got to find this double integral over some region R, but R is nasty, right? There's something wrong with it that maybe requires lots of integrals, got to split the region up, that sort of thing. We can do a change of coordinates very similar to a change of variable. What you do is you transform the region you're integrating over, transform it into a new coordinate system that's easier to handle, right? Then the limits are easier to find. So we usually do this problem motivated by the region we're integrating over, not the function we're trying to integrate. There is an example where we do that. That example is very hard. I'll go through that if we've got time at the end. But I'm not going to give you one like that, to be honest. Now, but the main thing is we can do this by performing this change of coordinates. So basically we've got x and y are written as a function now of two new variables. We call them u and v, just like we use u with change of variable in single variables, just second one now v. Right, so x is some function of u and v, y is some function of u and v, so u and v are my new coordinates that I want to do the integral with respect to, the double integral with respect to. And of course the order doesn't matter, I could do u then v or v then u, right? The idea that the order doesn't matter continues. And it turns out this is what you do. Now this is proved in the unit reader if you're interested, right? The proof is very convoluted and complicated, but it is in the unit reader if you are interested. But let's unpack what all this means, right? So basically what you're doing is you're replacing x and y with your new functions in terms of u and v. You replace your dx dy with this awful looking thing, right? Now this funny notation here, this thing here, this is called the Jacobian matrix. It's exactly what we were doing before with Jacobian matrices, right? Just different notation. The main reason we switch notation here is because when we do a change of coordinates in double or triple integrals, it's always square, which means it always has a Jacobian, right? If it's not, you need as many independent variables as like old variables as new variables, so it's always square. It's either 2 by 2 or 3 by 3. Anything else won't make sense, right? So this is the Jacobian matrix, and we set this up as, remember the notation we used before, where the first row is your first function, and the rows are your functions, your columns are your new variables, right? But remember, we used different notation before. We used this much simpler notation. With integrals, we switched to this notation. I honestly can't tell you why. I don't know why we do this, right? But this notation is actually a little bit nicer because it tells you the order. So you have rows that are U and V and columns that are U's and V's. Right? Right, so that's the Jacobian matrix. We need its determinant, so it's Jacobian, the Jacobian of this Jacobian matrix. Right, so that's what det means, short for determinant. Right, and these big things here, which we often use for determinants, does not mean determinant here. Right? These mean absolute values. Right? Because what's happening here is that these are definite integrals, they're numbers, they're volumes of some description, so we make them positive. All this means is if it gets a negative answer, you just drop the negative and make it positive. All right? Right, so, and the determinant of this is the Jacobian, which is what we did several weeks ago. Right? Beforehand we used slightly different notation, right? But it's the same thing. Right? And basically, put it all together, you get this formula. And notice the similarity, if you squint, right? More symbols and stuff floating around. But notice the similarity with what you do with a function of a single variable. Right? Right? So there's a couple of things to do. You need to figure out your new coordinate system in terms of your old one. So you need x and y in terms of u and v. You need to invert that, so you can find all the partial derivatives you need if necessary. Find the Jacobian, find its determinant, plug it all in, work out the new limits, and off you go. Right? Much easier than it sounds, of course. Right? Now, and again, these are absolute value signs, not determinants. It's already a determinant by the det. Right? Det short for determinant. Now, the proof of this is in the unit reader. It is several pages long and is very involved. But basically, you remember your dx dy is like a little area element. You can prove that when you map that area element, say it's a little rectangle, into another rectangle in a new coordinate system, right? So the areas are linked by this multiplying the two by this factor. That's basically what it is. It's in the unit reader if you're interested, right? Not for the faint-hearted, right? But it's in there if you're interested. The main thing is sort of see the similarity with what we do before, right? But as I explained, with functions of a single variable, our change of variable is not determined by, we don't give a crap what the limits are doing. We do it because we've got something we can't integrate. Most of the time, and the only questions I will give you on this is where it's motivated by the region we're integrating over. So the limits are what determine it, not the function. Right? But let me show you what I mean. Let's have a look at this example. It looks fairly straightforward. Remember when I said when we do double integrals, the very first thing to do is draw the region you're integrating over. So this looks pretty straightforward. You've got a simple thing to integrate, 3 times x minus 2 times y. And I want to find the volume bound by that surface that sits above this region in the xy plane. Right? So this region bounded by 4 straight lines. Right? And you think, oh yeah, awesome, easy. Then you draw it. Oh crap. No, not so easy. Right? This is the region we're integrating over. Right? Now, if I want to do this without doing a change of coordinates, note that I will have to do 3 separate integrals, won't I? Right? Because if I'm sitting over here, let's say I decide to integrate with respect to y first. Y would go from this curve to this curve, and x would go from here to here, yeah? And then, so that'll give me, that I'd have to slice it there, do a double integral from there to there, right? I would have to slice it there, do a double integral for where y goes from there to there and x goes from this point to this point. Then I would have to do one where I integrate from there to there, y goes from that curve to that curve, and x goes from that point to that point. That would require 3 double integrals. Right? You could do it though, of course. Right? How would you do it? Well, first thing, you draw it. Now obviously I'm cheating, right? But you draw it, that's what this region looks like. Right? I'd have to find all these intersection points. So that's basically x is minus 1 on 7, that's x is 2 on 7, x is 27 on 7, and this is x is 30 on 7. Right? Then I could integrate y going from this curve, which is minus 2, y equals minus 2x, so that's basically, oh, where did the lecture notes go? Where'd the lecture notes go? Oh, right, yeah, I'm at full screen, right? All right, so it goes from this one, so y goes from minus 2x to 3 on 2x plus a half, right? So that's solving this one for y. And x goes from minus 1/7 to 2/7, so that's this bit. Then I'd have y going from 3 on 2x minus 1 to 3 on 2x plus a half, right? So that's that one to that one, right? So that's that curve to that curve, and x goes from 2 on 7 to 27 on 7. And then the last bit, I've got y going from this curve to this curve, which is 3 on 2x minus 1 to minus 2x plus 14, right, which is this one. And x going from 27 on 7 to 30 on 7. So that's three double integrals, right, all with different limits. And of course the answer annoyingly comes out as 3. Right? Now you could do that, but there's a better way. Right? What if you could come up with a way where you could rotate this coordinate system? Because if you look at this picture and think, well, this is a rectangle. I mean, if I made it so it lines up with coordinates, life would be good, wouldn't it? Right? And there is a way you can do that. Right? Take note of how I've written them. Right? So you got the lines 3x minus 2y equals minus 1, 3x minus 2y equals 2, and then 2 other lines, 2x plus y equals 0, 2x plus y equals 14. What you can see is the first row, the left-hand sides are the same, aren't they? Right? And the second ones are the same. Right, so if I let u equal, hang on, let me make sure I don't stuff it up. If I let u equal 3x minus 2y, right, as my new variable, the first row is telling, well, u goes from minus 1 to 2. Yeah? If I let v equal 2x plus y, then v goes from 0 to 14. Right? So essentially I'm coming up with a new coordinate system that maps this to a nice rectangle that's all lined up. Right? Right? So once I do that, then my limits of u and v become easy. One integral. Right? Now I've been motivated by u and v in terms of x. I need x and y in terms of u and v to work out the Jacobian. But it's nice and linear, so that's fairly easy to do. If I solve the equations u equals 3x minus 2y and v equals 2x plus y, if I solve them for x and y, two equations in two unknowns, if I solve them for x and y in terms of u and v, I get x as a 7th of u plus 2v and y as a 7th of 3v minus 2u. Now I can calculate the Jacobian. Right? So the first row, partial dx du, partial dx dv, that's just 1/7, 2/7. Second row, partial dy du, partial dy dv, that's just, that's easy. Calculate its determinant, this times this minus this times this, I'd get a 7th. Right? Notice that this, if it's 0, then you're not mapping a closed region to a closed region, right? It ain't going to work. Right? So this will never be 0. If it's 0, you've made a mistake somewhere. You've picked the wrong transformation. Right? So it won't ever be 0. And we just make sure it's positive. Right? That's what the absolute values in our formula do. That means that I can work out the integral. I just replace x and y with u and v, right? And it turns out I just get u because I've made it easy. Right? Multiplied by the determinant of the Jacobian the 7th time, then du dv or dv du. It doesn't make any difference. Remember, the order doesn't matter. Right? And it comes out much easier, isn't it? And of course you get the same answer. Right? So here I've done it, I've had to do it with 3 integrals, all with awful limits. Right? And I've got the, and it, you know, Maple's telling me, thank God, that the answer is 3. And doing it this way, much nicer, right? So this one has been motivated by the region we're integrating over, and they're the only ones I'm going to give you. The harder ones are where you have something that you actually can't integrate at all, right? And you hope that it all works out, right? But I won't give you one. So I'm going to show you one, but we're not going to do one like that. Another very useful coordinate system, so that either it'll be motivated by the question, or it'd be one like when we were defining limits for functions of several variables. We saw polar coordinates. Whenever you've got some sort of circular symmetry, in other words, there's an x squared plus y squared or a circle floating around somewhere, polar will make life easier. Right? So quite often we do this with where the region we're integrating over is better described in polar coordinates. Right? So remember our polar coordinates, we replace x with r cos theta and y is r sin theta. So our new variables are r and theta instead of u and v. It doesn't matter what the hell we call them. All right, let's just stick with r and theta because that's what we're used to. All right, so if I've got, so this is just a review of all the polar coordinate stuff, but if I've got an integral that's better described like this, I need the Jacobian. We calculated this weeks ago when we were doing Jacobians. The Jacobian of the polar coordinate transformation is just r, right? So my integral in Cartesian coordinates can be done in polar coordinates by replacing x with r cos theta, y is r sin theta, and then multiplying it by its Jacobian, which is just r. Don't forget the extra r, right? Otherwise you might end up with something you can't integrate. Right? And we use this whenever the region's got some, basically circles in it. Right? Now, let's have a look at an example of this one. Let's say I've asked you this. Find the volume of a solid bound below by the xy plane, so that's basically the plane z equals 0, and above by the paraboloid z equals 25 minus x squared minus y squared. Right, so basically, in other words, what we're doing is we're finding the volume bound by this surface, 25 minus x squared minus y squared, that sits above the region 25 minus x squared minus y squared equals 0, right, the xy plane. Right? So I've got to find the volume bound by this paraboloid that sits above this circle in the xy plane. Right? Think, okay, let's try it in Cartesian first. All right, well, let's set it up. So that's the function I've got to integrate, 25 minus x squared minus y squared. And this is the region I've got to integrate over. Now, how have I decided to do it? So I could say, all right, y goes from minus the square root of 25 minus x squared to the positive square root of 25 minus x squared. So small sweep in y, and then a big sweep in x from minus 5 to 5. All right? So I could do, all right. But then when you get started, you realise, remember, square roots are never good in an integral. Right? I could do it that way. Again, I'm going to cheat. Right? If I do the first iterate with respect to y, right? If I just integrate this with respect to y, I just get that. But when I plug in the two limits, minus the square root of 20 to the positive square root, I get that. And that's what you then have to integrate with respect to x. Now it's doable, right? But it's not pleasant, right? But you can do it. So the first bit, they're basically all three, believe it or not, are inverse trig substitutions, right? So you could probably see that from this one and this. Remember, inverse trig, if you've got an a square root of a squared minus x squared, you let x equal a sine theta. Right, so if you let x equal 5 sine theta, you can work out the first one and the last one. You can actually also do the middle one. Remember I said the inverse trig substitution is very powerful. Although we only use it for square roots, it can be used for all sorts of things. You can make it work. Right, so this one, which technically has a square root in it, because you can think of this as being 25 minus x squared times the square root of 25 minus x squared. Right? You could do it. It's not pleasant, but you could do it. And you'd find that after a lot of work. Right? And then when you x do from minus 5 to 5, you get the answer. Right? But surely, because we're integrating this thing over a circle, there's a better way. Right? Now, how would I describe this in polar coordinates? Right? So remember, r is your distance from the origin, and theta is your angle from the positive x-axis going anti-clockwise. So you could think of this as, well, this is rather simple in polar coordinates. R goes from 0 to 5, theta goes from 0 to 2 pi. Those two will sweep out the whole region, won't they? Right? Nice constant limits, that's always good. Right? Right, so instead of doing this and having to integrate all these terrible bloody terms, let's use polar coordinates instead. Right, so r, as I said, goes 0 to 5, the radius of the circle. I need the whole circle, so theta goes from 0 to 2 pi. My function in terms of r is nice, 25 minus r squared. So now I've got my function written in terms of polar coordinates. I mean, sometimes there might be a theta floating around, sometimes not. This one's easy. Times the Jacobian bit, the correction bit. Some textbooks call this a density correction, right? But I just call the Jacobian correction, basically. The r, dr d theta, or d theta dr. A hint I give you, don't muck with the order, right? Always do this r dr d theta, always. Very rarely would you want to do theta first, or have to, right? Right, that's easy. I can do that, done. Right, that one's actually very straightforward and is a much nicer than having to do it that way, isn't it? Right? And so I'm cheating here, but you know, this spits out the answer relatively quickly. Right? But of course, you know, we don't work that fast by hand, right? And of course you get the same answer. Here, doing it in Cartesian way, which would be a lot of work by hand, I get 625 on pi on 2, and hopefully, which I should have checked, same thing, of course. All right? But there could be other ones where Cartesian will be impossible. So for example, if this one spat out, if you change this even slightly, go away. Let's say I change this to Oh, that's not too bad. Let's say I change it to, oh, here we go. If I do that one, yeah, whatever. Right, whatever. It gets complicated, right? Whereas polar makes it much easier, and it's very, very easy to make it impossible. Yes? No, the bounds will still be, oh, yeah, good point. No, they wouldn't be. No, because then no, they wouldn't be. So I should leave that as is, shouldn't I? Yeah, whatever. Right? You get the idea, right? The key is polar has made it much easier. Yeah? So let me just change all that back so I don't forget to do it later. And of course you get the same answer. Right, so these sort of problems for double, next week we're going to do change of coordinates in triple integrals, but we'll only do 2 specific cases of new coordinate systems. But with double integrals, if I ask you to do this, either it's polar or the region will be implied by the question. Right? The really hard ones are ones like this. Right, let's have a look at this one. This is I will not give you one like this. Or if I was going, let's say I'm not, right? But if I was, I would give you a hell of a lot of hint with this one, right? Right, let's say we've got to evaluate this double integral and I've got to integrate over a trapezoidal region with those vertices. And I'm using the shorthand, it's not shorthand, I'm the opposite of shorthand, using exp for the exponential function. So I've got to integrate that over that region. And immediately there are lots of problems, right? First one we notice is, remember what I said, always draw the region first. Even before looking at the frickin' integral, draw the region, right? And we see the first problem. Well, no matter how I do it, I need to do two integrals. If I decide I'm going to integrate with respect to y first, I'd have to split it here. And then between x goes from here, 0 to 1, y goes from this curve to this curve. And then from here to here, x goes from 1 to 2, y goes from this curve to this curve. Right? So two integrals, crap. Right? Or if I did it the other way, if I wanted to integrate with respect to x first, same problem. I'd have to split it there. From y from here to here, x goes from here to here. And then y from here to here, x goes. No matter how I look at it, two integrals. And you go, oh, you know, that's the first problem. What's the second one? Can you even integrate that either way? You can't, can you? Right? If I asked you to integrate, you know, replace y with 1. Let's say I asked you to integrate e to the x plus 1 over x. That's impossible. Can't be done. Let me just prove that. So let's say I asked you to integrate that with respect to x. Right? Again, this is one where I can do it, right? But it involves functions you've never heard of, right? And we've seen this this is the exponential integral function, not something I expect you to know about, right? Right, so for our purposes, not only would the region require two integrals, I can't even get started. And if I integrate with respect to y first, it's the same function basically. It's y plus a constant over a constant minus y, same problem. Right? Alright, so I can't do this either way. Right? So my only hope here is, well, try this and hope, and so this one, the change of coordinates is motivated not by the region, because you could see, well, surely I could map that to a rectangle. Right? And you can, but that's not going to help, because the mapping that makes this a perfect, nice rectangle will make this worse, right? And leave you something you still can't integrate. Right? So this one is one where this motivates it, right? So, and then you just hope and pray it works, right? So looking at that, well, one obvious thing to try, right, would be, well, let's say I let u equal x plus y and v equal x minus y, right? Then this would come e to the u on v. That I can integrate with respect to u, can't with respect to v though. You can't integrate e to the 1 on x, right? Again, that one's involves things you don't know about, right? So essentially that's all I could try. Let's try and let u equal x plus y, right? Then I need x and y in terms of u and v. Now I've got to figure out what the mapping looks like, right? So to try and figure out what this is mapped to, right, I need to go along and map, well, what happens to this line, this line, this line, and this line, right? And when you go through all the process, it turns out it's mapped like so, right? Which is it's not a rectangle, but it ain't too bad, right? So it's another parallelogram, what's the word I'm looking at? Trapezoid thingy, right? And that's not too bad, but I'm forcing myself to integrate with respect to u first. So I see u's got to go from here to here, and v's got to go from here to here. And I just hope it works, right? And you need the Jacobian. This one turns out is negative, so you just drop the minus sign. Right? Right, so this becomes e to the u on v times a half times the u dv. And I can see that, well, I can integrate with respect to u. There might still be an issue when I then try and do the v1, but like, fingers crossed that it works out. Right? And of course, I've designed it so it does. Right? Now, when I integrate with respect to u, I get something I can handle. Right? And because it turns out this one, the u on v, because it's u on v and u goes from v to minus v, they just become constants. That gives me something, and I can do it. Right? These are the really, really hard ones, though. Right? Because you need basically you need all the planets to align for this to work. You need the function to integrate, and the region to be closed, and the region to be doable. Right? So these ones are really, really difficult ones. These are not what we're going to be doing. Right? The way we're going to do these ones is either like this one in the lecture notes, where the way I've written the region makes it obvious what to do, right? Or like this one where the region you're integrating over is a circle. Polar always makes life easier when you're dealing with circles, right? So work through those two, okay? This one, do have a look, but this one is very challenging, right? And I'm not going to ask you one like this. This is an example of a very, very nasty one, okay? All right, I think we'll leave it there for today, okay? So do give this one a look if you like, but concentrate on the other two examples, all right? We'll leave it there for today, and I'll see everyone next week, okay?